green super rice varieties for changing climatic conditions by Dr. Jauhar Ali, the International Rice Research Institute, the Philippines. He completed his PhD program at Indian Agricultural Research Institute in New Delhi and was a project scientist at the International Rice Research Institute. He is currently a senior scientist and plant breeder at the institute. He received the plaque of recognition for serving at the Rice Research Institute of Iran. Ladies and gentlemen, please welcome and congratulations.
Yeah, thank you. On the onset, I'd like to thank the organizers for inviting me and allowing me to present this work that we did in ERI. We know that why there is a necessity. I did not elaborate more on that, but still to highlight some of the key issues, that was the food security was a looming threat after we had the one in 2008 when the food shortage was experienced in more than 72 countries, and the pressure of producing more under ever reducing resources of land, water and labor. But if you have to see in the future that we have to develop stable and sustainable yields using lesser inputs. Here lesser inputs I mean is site-specific nutrient management at least, and a farmer practice, rain-fed. We have to see how we can tackle the rain-fed the complexity of most of the abiotic stresses, and under stressed conditions we need mostly the varieties will be requiring the lesser inputs. And if you see the disease and insect pest the threats that we see with the high input environments over the last few decades, we see that it is mostly by the high input environment, especially in China, where more than 250 kg of nitrogen is being used. We also experience the threat of these breakdown of resistance, and we need broad spectrum resistance sources with durable resistance at least. And of course, everything comes with a price tag of much of the chemicals that are used either as fertilizers or chemical pesticides ends up in your plate. So we have all the time we have to see how these can be reduced and make. And the topic which I will be talking about is basically on the climate change. And we know that the vulnerability is much by one single factor of temperature. Higher temperatures has its own consequences on the high greenhouse gas emissions, and thereby creating a cascade of effects. And how we are going to go ahead is we need multiple abiotic and biotic stress tolerance at the first place. We know this is what we are seeing is we see the pests, all the flooding, the coastal lines are susceptible to the inundation of the coastal saline areas, especially in the delta regions, and also the BPH in recent times. So it's like a race against time with a lot of hurdles in this. If you see this particular the drought stress frequency, which has been mapped from 1960 to 2002, we see the areas that have frequent drought experiences. Likewise, in case of the flood frequency in these regions, where more than 75% is seen in Bangladesh. And if you see the resources that we are having in hand and the population growing in a rapid scale, we see this oil is not going to be ever. So much of the fertilizers are going to be dependent on this particular thing. And so is the phosphorus fertilizer coming from rock phosphate is not going to be ever. So this is the things that we have in hand, and based on this, we need to develop something, what we call as the green super rice. In this particular aspect, we like to target the rain-fed and the irrigated lowlands, especially the coastal deltaic regions, especially in Bangladesh, Vietnam, and most of the delta regions. And then if you see what we mean by green super rice is the rice cultivars that will produce higher and more stable yields with lesser chemical inputs, that is water, fertilizer, and pesticide. This concept was earlier given by Kifa Zhang in 2007, but this is a non-GM approach that we are adopting at IRRI, and though in the overall picture everything is included, as Kifa has pointed out earlier. So what we are intending is basically to try to combine many of the multiple abiotic stress, just like these ones, not into a single line, but kind of varied kind of permutation combination, so that we can effectively cover the target regions. So one such would be the high resource use efficiency, especially water and nutrients, is one of the primary target traits that will reduce the fertilizers and water intake. And the useful combinations that we see is drought with salinity, drought with submergence, salinity with submergence, drought, salinity, and submergence together, all with the good grain quality that somebody, one of the earlier speakers had pointed out. Nothing will work without good grain quality. And another issue is the low gelatinization temperature. The low GT can save 10,000 years of fuel. As per Melissa, one of our quality lab in charge, she said that if you have low GT, it lists 4 minutes less cooking time, and you can multiply that over every day, which will run into 10,000 years of calculation, I don't know. But what we here mean by the green super rice is we like to maximize the grain yield under limited supply of nutrients and water. At the same time, we like to increase the yield potential under sufficient supply of nutrients and water, which is quite contrast to the super hybrids and super rice concept, where everything is done under ample or more than required fertilizer or high input environments. To start with, I'd just like to highlight one of the very key slides that we did in the past from 1998 onwards, when Zikang was there, on the drought, where we had pyramided 2 rounds of pyramiding on using the design QTL pyramiding approach, and we developed many of the pyramiding lines. And these pyramiding lines showed, some of these lines showed the nitrogen use efficiency or the fertilizer use efficiency, as well as the drought tolerance. So we placed this into 6 locations, and we plotted as an AMI by plot, and we can see some of these lines doing very well as compared to the checks. Over the best check, and you can see the line is more than a ton. And this is the Sahbagi Daan, which was released a year back in India, and this is Apo across these locations. So what I mean is, by this breeding approach, we developed many good lines which are under testing now. Now this is one very important slide that out of these 20 of these pyramided lines, is 11B, which is already combining high protein of 11%, 21% of amylose, and it is good for drought, salinity, cold, BLB, and blast tolerant. And this was a very big plot size in Indonesia. But before that, I should like to emphasize what we really mean by green super rice concept. If you see the 11B here, which is under 75% of site-specific nutrient management, that means as the farmers, based on the soil data we give, so this is 25% than the recommended. That means this is the 100% is the site-specific, and this is higher than the check, that is Sehrang and Impari. So this makes it, the yield of this, when it is higher than the check of 100%, that is what we mean by the real green super rice. That means you save 25% of the fertilizers. So first chemical advantage that you get is what I mean here. The second thing is, before we go on, I just like to highlight, illustrate how this new innovative breeding strategy helped us to breed this type of materials. This concept again was tried to confirm in from 2008 wet season onwards, and within a short period of 3 or 4 years, we have developed many lines with multiple abiotic stress, and this is what I'm going to present now. So we took about 16 donors from HSE background, and we screened BC1F2 for varied stresses from the normal condition to less input, upland, the anaerobic condition, the submergence, salinity, everything were screened, and these interpretations were fixed over 3 rounds of selection. And after fixing them under very severe screening strategy, the survivors were pooled, and every time we were screening it for all the traits, and quickly brought it to the preliminary yield trial, and they replicated, and within this short period we could do that. Now, once these integration lines of our particular background, then we can combine them into the for the design QTL parameter. So these are the 16 of these lines at this dry season of 2012. These were the 2 batches of the 16, and if you see how we moved from the 2008 wet season, you can see for different screens we genotyped, and then again we moved, again combined them, and finally we brought about 108 to the preliminary yield trial, 68. Finally we put 2 of them in the national trial and 29 in the MET of the multi-environment testing. And if you see, now these lines have been whole genome sequenced, all the 497 of these introgression lines over 8 populations. And the interesting thing is that we see the introgression of different donor sources vary, and this is very interesting. Despite their varying, but they have much of the drought, salinity. They are not sources for drought or salinity or any of these traits, but they contributed to these traits. So there is a hidden genetic diversity which is there, and when you have these selection sieves, strong selection sieves, they get selected. And this is what is the highlight of this. None of them are actually drought or salinity tolerant donors in the first place, but they contributed to these traits in a very different way. And we are now trying to understand this by what we call it as the networking. We are trying to establish the mapping of this in a different way, which Zikang has developed a new methodology. But to highlight this issue again, we see about 845 lines, introgression lines, out of which 146 were put into the RYT and PYT, and out of 40 were in the national coordinated trial of the Philippines and the MET. And out of this, we had 2 of them in the NCT, which is already nominated, and with triple traits, drought, salinity, and submergence in one single line. 2 of them, and 1 of them stood first in the MET of the GRISP stage 2. So this stage 2 was done at 5 locations, and this with these 3 traits plus the yield under irrigated, it stood first, and that is itself is a answer to this strategy. And this came from Falguna, basically an Indian variety, and this is a Chinese variety. Coincidentally, we are trying to now understand what kind of introgressions led to this kind of enormous potential of combining drought, salinity, submergence, yield under low input into one single line. Is the to understand that, we have to go into the details of this sequence data, which will be shortly done. But then what we did further is, now we are already after we are going for the design QTL parameter using that particular line, and we have already developed BC1, the F2 population, and we are at this stage screening again, and then we will again try to understand how we can improve further that particular line for more traits. Now, this is some of the samples that screenshots at the different conditions. This is under low input conditions, and if you see some of these lines, this is the drought check. You can see the drought check, which gives very high yield under drought, and under normal conditions it's 4.2. But this is the line I'm talking. You see this particular line, which is 1.4, and it is comparable for the drought. At the same time, high in the irrigated, and also good in the low input conditions. So you can compare with the hybrid, and this is the check, irrigated check, this is the Apo. And this is a very high level of drought stress with 300 kilopascals of drought stress, where plants die generally, and Apo could not flower at that stage. And you can see this plant is very comfortable there. So this kind of drought, the kind of screening that we did has enabled us to prove the concept. Now, most of this particular line, I will be talking much about on this particular line, where we combine the triple traits. And you can see many of these traits under drought or low input or irrigated, they continue to do good in all the three conditions. They don't do that means in one condition they do good or bad. We select only those lines which they do good in these three conditions. Otherwise, we don't forward them. And then this is for the BPH tolerance. We try to prove it in Indonesia that this could be done for any trait. Within a period of 2 years, we have already developed introgression lines confirmed for BPH tolerance without any known donor source. And this is what it's all about. So in the selection strategy, basically, when you compare with the conventional, with the GSR breeding strategy, we have wider adaptability. It has a slower rate of breakdown for pests and diseases. The genetic response is to the use efficiency, and it can be applied to any condition, making it not specific to irrigated or drought. And this is that line which I'm talking about, is the highest yielder, and it gave 10% over RC222, which is under the GRISP stage. And this is the data that we have been following right from the several seasons, and it stands on the top of these lines over the mean. And this is the MET data of the stage 2, where it gives 6.31 tons against the checks that were used in these conditions over 5 locations. And we found that the radiation use efficiency and nutrient use efficiency of this line is enormous, and we will be following this further. To prove the salinity tolerance, this is the slide that shows the salinity tolerance is 7% over the national check of the salinity check of the Philippines, and this is 7%, and we have all these lines available. And this is the screen which Bert Collard, our colleague at ED, had screened this, and we found many lines with triple traits that are tolerant to submergence. And this line is here with the triple trait, which scored 4.3, moderate submergent tolerance. And again, this is at the farmer's trial at a big plot size. It gave up to 26% advantage over the checks, and but we claim only 10%. But this is a very big plot size. And in a nutshell, if you can see the comparison over all these conditions, the mean of wet season, the wet is 6.49, and you can compare it with the check here, and the low input condition under rain fed, under drought, under salinity, under on-farm trial, under submergence. So the relative advantage of these lines. And these are the 4 promising lines that is ready for the climate change. This combines drought, salinity, and nutrient use efficiency. This combines drought, salinity, submergence, and nutrient use efficiency. This is an aromatic line, drought, salinity, nutrient use efficiency, and low GT. And this is a line which is salinity, submergence, drought, and nutrient use efficiency. And these are all going to be released possibly in 2013 in the Philippines itself. So these are already advanced into the 3rd or 4th stage of the screening in the Philippines. And this is the line that I was talking, which has a very immense potential in Indonesia, and this is a big plot size of 2.5 hectares in Purwakarta. This is the line that I was talking about, the combining the drought salinity with aroma, as well as GT is low and protein is 9.4%. This is that line I showed you before, which is doing very well in many of the sites. And to be on the quality, we have a very good spectrum in the introgression line to fit and match any country that we require to target. So it's not that we only target any country. We can design and customize it for any country that requires a given quality. So when we tried the aromatic line, and it was judged as the best across all the farmers who used this line. And with that, let me thank the director of the GSR project, Zikang Lee, and there is a ED GSR team comprising Noli, Glenn, Choi, Redonia, Walpade, Andy, Peng, Krishna, Wang, Tao, Li, and a GSR team from CAS, which also helped us during the initial time for this thing. And the GSR MBL team, my own group, Jello, Corinne, Pauline, Denver, Macro, all these guys are made this thing possible. And with that, I'd like to thank you for your attention.
We have time for a quick question. Yes.
Okay, that's a good question because what we did was you should understand that this is not just the last few years, but in 1998 onwards, when the International Molecular Breeding Program was started, we were at the developing with 3 recurrent parents and 200 donors. We progressed from 200 donors into 3 recurrent parents. That is the experience. We found that any donor you use, you can get transgressive segregant invariably at around 70 to 80% of the donors contributes to transgressive segregants. So you can get from any source, no need of worry that this particular should be a donor. But if you have a specific donor, it's advantageous to get for that particular trait, but you lose other traits. So that is the reason we should not use specific donors. Only you can improve that particular trait, but not other traits. So that is the reason when you screen even from susceptible donors, you can get tolerance from them. For example, FR13A, many of you know it is a submergent tolerant, but it gave tolerance to salinity too. Likewise, TKM9 is a drought tolerant material, but it gave tolerance to submergence. And when you screen these material directly under submergence, they die. So is the FR13A. When you screen for salinity, they will be killed. But when it comes in the IR64 background, it survives. This is the transgressive segregant we are talking about. So there is an immense potential of this simple technique, and anybody can adopt in any place. And this is a simple breeding stuff. But only thing we can improve it by molecular breeding by using the marker, the SNP markers. Then we can track it, which regions will be more favorably combined. This can be very enormous potential it has. So already we have demonstrated these lines, and we have enough now. The design QTL pyramiding that we are doing has still more to come, which will be more advanced ones.
I can't stop asking this question. Shigang Li as well. Okay, so you want to say that by using good and large number of parental lines, phenotypic selection is more effective than using target QTL, right?
Yeah, the phenotypic selection is the key to success. As simple as that. We used a very severe screening strategy, very, very severe. We wanted to kill because we had a lot of populations in the first place. So we cannot handle those populations. So we wanted to mercilessly kill them. So increase as much drought we could, as much salinity possible. Then we were killing it basically to remove all those lines which it doesn't survive. And the few lines we survived, we moved with that. So that's as simple as that. There's no secret for that.
Welcome. One more.
So for this program, just working together, see a lot of backcross.
Only one backcross. This one is shown with one backcross, BC1. Yeah, but in this case, the second round we did was only 16 donors. Yeah, we are having. Entire stock is with us. Anybody who is interested to share, we are ready to share these materials to any country, anywhere, whosoever likes to use these materials. They just can write an email, that's it. And already these are working in many countries, and in the many national coordinated trials, many of these lines have been identified. So we will expect something like in 2013, many of the varieties will be released, because already it's 3 years from now it's being tested. So it should be, many of these lines are doing very well. So it's not that just we are talking about some QTLs and genes. I don't believe still those QTLs and genes, because ultimately you need a product in hand. That's what the farmers need. So as far as that is concerned, we are scoring on that.
Thank you very much. Please give him a big hand.